Hi, welcome back guys to this video on HYSYS, this video series on HYSYS. Okay, so in the last video we actually talked about how to use the case study function in HYSYS to do some optimization, and we didn't quite optimize our reactor system due to time. Yeah, you don't want the videos to be too long, but that was just a demo to help us, understand how we can get how we can optimize our system. So we want to move on to the next part, which is how do we get our CO2 fresh feed. Now obviously, if we're going to purify flue gas, we can't expect 100% composition of CO2. If we can't expect 100% composition, how much should we be expecting? So now we have to begin by talking about flue gas purification. We want to take a look at typical flue gas composition, and as seen here, let's say from a coal-fired power plant, the temperature of flue gas will be about 160 to 180 degrees C. Its pressure is about 1 atmosphere. Volume is about 23% water, about 11% CO2 by volume, O2 about 5%, sulfur dioxide about 200 ppm, you just take the high amount, and the NOx, the nitrous oxides, that will be about 250 ppm. So we'll just assume 99% of that is nitrogen nitrous oxide or nitric oxide, I can't remember what's the name again, NO, yeah, NO. 99% is NO, the balance is NO2. So let's just take a look. Okay, so this is a flue gas composition, and what's the conversion from ppm, let's say, to ppm to mass percent. So well, the thing is that 10,000 ppm is about 1% by mass. So we'll just take that into account. Just use that to kind of estimate what we want. Estimate our flue gas composition. So let's just copy this image, and of course we have this from ResearchGate. I have to cite whoever. So yeah, Artano et al. 2012. Okay, so that's the guy. Okay, so I just cited it by mouth-ish. Oopsie. I'm going to copy the image over. I'm going to put this in Excel to, let's see. Yeah. So we put this in Excel to see how much what our flue gas composition is. So we have O2, CO2, N2, H2O, CO2, O2, SO2, NOx. So nitrogen is whatever remains. Oxygen, water, we just put 11%. CO2, what's CO2? About 11% as well. Okay, water is 23%, or 22 to 23%, so I'll just leave it as 22%. Oxygen 0.05, SO2, let's say it's 200 ppm. NOx 250. So NO2 is 1% of the 250. 0.01 times this. Then I'll have this times 99. I want to go to 99%. The rest will be NO times 99. So 247.5. How do we change it to, let's say, how do we change it to mass percent or mole percent? So volume percent is nearly quite similar to mole percent, so I'll just assume it's mole percent. So by mass, all these will be in ppm. So ppm has a direct translation to mass percent. Okay, so it's equals 200 divided by 10,000. So equals this divided by 10,000, so on and so forth. Okay, so that's a very low mass percent. And let's just take what 100 gram basis, I suppose. Never mind. I'm not going to be that accurate. I'm just going to assume all this is in mole percent. Alright, so I'm just going to port this over. Okay, I'll port the values over, so just paste values only. That's just an estimation, yeah, so it's not reflective of true blue flue gas, but at least it gives us some kind of estimate. Yeah, I don't want to take too long to be accurate about things which shouldn't be that. It's not of that much importance. This is just for demonstration of HYSYS. I don't want to be that calculative. Yeah, so it's 99% N2, 55% H2O, and the rest are as follows. And so let's concoct our flue gas. The flue gas should be using the acid gas package. Temperature 180. Okay, pressure 101.3. So our water will be 22%, as said before. CO2 11%. CO just put 1%, just for the sake of putting it there. It has to be there somehow. O2 5%. Where's oxygen? Oxygen's here. 5%. Nitrogen 55 of the memory. Just SO2, I'll put it about 2%. SO3, I'll just leave it empty. H2S, empty. NO2, let's take a look. NO2, it's about, oh, that's really, really small. 0.025. So let's take a look. I'm just going to copy this over and paste. Okay. And NO will be here in Excel. Okay, this should be NO2. This is NO. Yep, and there you go. That's our flue gas composition, roughly. Okay, so flow rate. Yeah, unsure, we'll just give it 1000. And how much flue gas should we be using? This is raw flue gas. How much flue gas should we be using? Well, we want to have a CO2 feed of about this much, 225. So we need to make sure we have slightly more than 225 kg mole per hour of CO2. So let's take a look at the mole flows. We have 111, so we're just about triple that, 3000 kg mole per hour. And that should about do it. 670, 335. That's what we want. So we have raw flue gas from, let's say, a coal power plant, and we want to convert that to methanol, right? So this is the kind of temperature we should expect. Now, first things first, what do we need to do? We take a look at our composition. We have water, we have CO2, we have CO, N2O, NO. Okay, that should be okay. I think I make a mistake. Mole fraction. I need to swap this out. 0.25, 0251, and okay. Yeah, NO should be 2.5, and the rest are as per normal. Okay, so these are the things you need to look out for. And yeah, so what do you need to deal with first? Well, the temperature is pretty high, and that's a good thing because we can use that kind of heat. The pressure is a bit low, meaning to say we'll have to compress it we'll need to compress it so that we can force it through our absorption tower. So in this case, yes, we are using amines to extract this CO2 out. Okay, we're using amines. So we have gotten our flue gas and we're just using amines to get our CO2 out. But the thing is, if we use amines, we'll have lots of other acid gases as well. Let's say sulfur dioxide, NO2, which we definitely do not want in our system. So we'll need to find a way to get rid of them first. So now what do we do? Basically, we need to wash out that SO2 and that N2 or NO2 from our system. So basically, we kind of guess, because SO2, sulfur dioxide, and nitrogen dioxide, they're way more acidic than CO2, and the presumption is that, hey, they can be dissolved in water. So why not let's just use water to wash them out? It's a pretty simple trick. So that's what we can do. But first things first, we will need to compress this gas, let's say to about 3 bar, and we'll want to cool it down to get rid of the water. So let's do just that. Let's have a compressor. So I have a flue gas compressor. So we don't have a choice. It's all flue gas, so we'll need to invest in this compressor. So I'll have one stream saying compress flue gas. So I'll need to put it, let's say, about 500 kilopascals, because there'll be lots of heat exchangers later on. Then we'll have a flue gas compressor duty. Let's see how big this is. Okay, that's about 8217 kilowatts. So that's quite a lot of energy that's required. I can see the compression is way high. It's at about 470.8. Meaning to say we can probably recover some of that energy. Okay, so no worries. We can actually use this to generate some high pressure steam first. So we can use this heat exchanger, HPS generator from flue gas. So high pressure steam is very valuable commodity. We want to generate as much of that as possible. So let's go. We'll use the simple weighted as per normal, 100 kPa each side. We find that of course in the actual model, heat exchanger, it's a lot less. So let's just draw these streams out. Condensed HPS. Okay, never mind. Flue gas condensed HPS. Okay, just gonna speed up. I'm gonna use the utility ASME steam, and this will be ASME steam. Composition 100% water, and let's get 250 degrees at 4250. And this will be semi-cooled flue gas. And let's put a temperature to ensure the delta T min. We'll just cool it to about 265, thereabout, 265, 267. And here we will have fully vaporized high pressure steam for about 687. Which is good. We can use it to recover some of the energy generated HPS from flue gas. So from compressor. Okay, so not too bad. So we have a stream at about 265. It's still pretty hot, and we can use it for like heat integration and so on later on. So what can we do? We can further cool it down in one of these heat exchangers. tentative heat exchanger for okay, so we can bring it down to about 70 degrees C, and the pressure drop again, we will use 100 kilopascals each. This is a gross over estimation, but we'll make sure, you know, our streams are quite safe. So we'll just assume all our heat exchangers are using cooling water now, including this one. So I'll just like put cooling water here first. Reactor, cooling water for reactor, I just put at CW. Okay, it's completely liquid, so vapor phase fraction 0. It's going from 32 at about 150 kilopascals. Okay, shouldn't be 150, 250 then, because it'll be dropping by about 100 kilopascals, but actually it's not that much even. So 150 kilopascals. Okay, so it's all water, temperature about 35. Okay, so that will be the amount of water you actually need to use. But just for now, we'll use water, but later when we perform heat integration, we'll have to do something else. Okay, so again, water is used to cool. Yep. So let's put CW from, okay, Flue. Okay, so ASME, again I'll go from 32 to 35. Okay, pressure 250, this is just arbitrary, trying to speed things up. Okay, out will be 35. Okay, there you go. Just a tentative heat exchanger. We might want to optimize or do something about it later, but this is cooled flue gas. And of course, we probably want to use an air cooler as well. Flue gas air cooler. This is probably going to be quite big. Yep. Yeah, it's going to be quite big. So cooled flue gas. So this is going to drop, let's say 100 again. And the temperature is going to be about 50. We want to keep it at 50. Okay, so that's part 1. We have it at about 200 kPa. And we probably want to have a bit more. So we need a bit more pressure, perhaps. But maybe we'll do that later. Okay, so that's just preparing the flue gas at the correct temperature at pressure. So this is a 2-bar cooled flue gas, and the first step is probably we want to do washing out using water. So this is the first of many distillation columns you'll probably use, or absorber towers. So this is the absorber, and as in every absorber, you know, the gas will come from the bottom and the liquid will come from the top. So this is there's a gas and liquid mixture in here because there's some there's actually some water. There's a vapor phase and a liquid phase, aqueous phase. So some of it will have to come out as water. So we'll call this wastewater out. Water will go from the bottom. Then let's wash this flue gas using water. So let's just call this water in. Okay, water in, and the overhead vapor outlet will be washed flue gas. So let's go next. Top stage pressure. So what should it be? We'll just have an initial gas of 150 kPa. Bottom stage is about 190. So it's about 4 kilopascals per stage because it's a 10 stage tower. You can see it's a 10 stage tower here. Actually, we don't even need that much. Maybe about 5. This is just an initial gas, so don't have to be that accurate. Top stage, and give and take 50 for both. This is optional, but it helps it to converge better. So this is your tower, and the water, it's not going to converge because we have not defined this yet. So this is coming at 32, pressure about 150, and it's all water. Okay, so that's washing water, and we're going to give it a molar flow, give and take 3000 first. That's just 3000. Okay, give and take. And then we're going to call this the water washing. Okay, let's try and run to see whether this thing can converge. Okay, it can converge, so that's not an issue. So we have some of the flue gas coming out, and significantly less water, which is good news. More CO2. Can see that there's barely any NO2 left. Can look at the mole flows. Barely any NO2 left because most of it has just dissolved. You can see that there's quite a fair bit of SO2. Now that's not what we want. So what can we do about it? Maybe we can increase the number of stages to 15, so we can run. So we'll have 190 at the bottom again. Let's see whether it dissolves. Okay, it doesn't quite dissolve. Alright. Let's increase the amount of water to see whether it can wash it out more. Wash more of the SO2 out. Yeah, so by doubling the amount of water, you can see that we are actually washing out a fair bit of sulfur dioxide. So we want to wash out as much of it as possible. So maybe 1E4. 10,000. Okay, that virtually eliminates pretty much all the SO2. And you can see the wastewater, all the SO2 is over here. So that's good. So this is just water absorption. Okay, so let's just increase it a little more just to be safe. So now basically all the NO2 has been washed out. Some of the CO2 has been washed out, and most of the SO2 has been washed out. Okay, so this is just a preferential absorption. Okay, so we have washed flue gas at about 32 degrees C. In fact, you can see that the washing water has effectively cooled the flue gas so much that you don't really need this air cooler anymore, basically. So that's good. That's good news. So let's just delete this away. Because you see, when this water comes in direct contact with the flue gas, most of the heat here is transferred to this water, and the wastewater out will do its job. So this actually carries the heat away. Okay, let's just run to see where they converge, and it does converge. Okay, so again, minimal SO2, which is good news. So basically it didn't need the cooler. Now take a look at this. Flash results are within tolerance but may be unsatisfactory because the EOS liquid volume was used for the liquid property calculations. Now sometimes you have this kind of warning, and you have this flash calculation has driven the pressure up to the upper limit. So what's going on here? Well, we can see that before we had that problem. Okay, let's put back our cooler. So input air, cool, flue gas. Let's put at 55 maybe. And the pressure, let's put it at 100 again. Okay, let's connect to this bottom, and let's press run. So you see it's converged without an issue. So what's actually going on here? Probably is saying that the temperature is too high for absorption. I mean, that's my guess. I'm not that sure of the actual reason, but if you do have that problem, just check your temperatures to see whether it's suitable. That could be one of the ways to debug. Now I haven't actually gone in depth. Maybe I can explore that in another video. But we have been at this for about 26 minutes, and we have actually gotten pretty pure flue gas. So with some water, some CO, NO, and some other stuff, which we will want to separate out. So in the next video, we'll actually talk more about the amine absorption tower. So thanks for watching, guys. I'll see you in the next video. Bye bye.